Hi, today I'll be talking about Lab 1 in physics, which emphasized the topic of constant velocity. The purpose of the lab is to create an experimental model of an object moving at a constant velocity to analyze the motion and compare this movement to a computational model. This experiment uses the fundamental principles of Newton's second law and helps deepen the understanding of those concepts throughout the experiment. So it uses Newton's first law, as an object in motion will stay in motion, or an object at rest will stay at rest, unless a net force is acted upon it. In this experiment, the object rolling is moving at a constant velocity because of this principle. In Newton's second law, the net force acting upon an object is directly proportional to its acceleration and its mass. In this experiment, there is no net force acting upon the object, thus it is not accelerating. And this can be seen in the equation F equals ma. But Newton's second law can also be derived to the equation of F net equals delta P over delta T. And delta P equals delta V times mass, so F net equals delta V times mass over delta T. We also use the position update formula and velocity update formula, as those values are relevant to this topic. So within the experiment, we have the system, which is the rolling object, and in my case, the chapstick. Then we have the surroundings, which are external forces on the object, which are friction, the force applied to start the motion of the object, air resistance, and in this case we assume air resistance and friction are not being applied to the object in motion, as it is supposed to have a constant velocity. The initial conditions is that time is at 0 seconds and the position is at 0 meters. And this lab showed how predicted and experimental velocities differ between an object due to outside factors, but that an object at constant velocity has a linear position time graph given the nature of constant velocity. So the procedure was to film a clip of an object moving at a constant velocity, upload the video into Tracker to create an observed model for the position of the chapstick over time. Then, after taking the results from the Tracker and doing calculations, you can use the starter code and plug in to create a computational model. Then graph both the computational and observed model to compare and see the differences. So within Tracker, as you can see, I've imported my video, and it gives you a graph which is fairly linear but still does have a slight curve to it, as well as a data table of the time and the position, which we can then put into Google Sheets to analyze. Additionally, it gives us values that we can use to calculate our initial velocity. So the initial position is essentially 0 meters, and the total time is 0.228 seconds. So we calculate the initial velocity by doing delta r over delta t to get 0.3917 meters per second. We then take this value and plug it into the computational model. On line 36, you plug it in to the ball velocity vector. Additionally, we leave the net force at 0 because object at a constant velocity has no net force. In my observed versus predicted models, the computational position graph is an underestimate of the observed position graph, and this is likely because of the push I gave my object, caused it to accelerate in the beginning and then slowly start to decelerate. So you can see at the end is when the computational and observed graphs are more in the same plane and more equal. And this is because the initial position is 0, so then the constant velocity was based on the final position and the final time, so that's the time where the computational position is a more accurate representation of the observed position, as shown in the graphs here. Some sources of error are other forces. So while we assume there are no net forces acting on the object in motion, in our everyday system there's always resistance and friction, which lead to error and alterations in the constant velocity. Additionally, while tracking the object on Tracker, there might be slight discrepancies in where the tracking point was placed, leading to small shifts and changes in the position versus time. If the axes were flipped, then the slope of my graph would have changed, because in my experiment, the right direction was positive x and the left direction was negative x because my object moved from right to left. But if we flipped the axis, it would move in the negative direction. So the magnitude of the results would stay the same, as the values are not changing, but the sign was flipped, so it would be the same, just in a different direction. And it means that there's not possible to determine the pushes and pulls to achieve a net force of 0 in the observed model. This is because we can't remove the effects of air resistance and friction within the observed model, but it isn't moving at an exact constant velocity and there are slight changes. But the computational model is able to estimate the constant velocity of the given object while no net force is at play by setting the net force to 0, which you can see in the graph. Thank you.